A property of numbers, or in particular integers, that we take for granted is that they can be broken down into a product of prime factors in exactly one way, or in other words, this factorization is unique. It may appear to be fairly obvious that this is the case. I mean, if we take a number and keep splitting it up into factors, and split those factors up again, it seems reasonable to guess that we'd eventually land at so-called irreducible or prime numbers, which can't be divided any further. Also, how could this process even lead to two different prime factorizations of the same number? What we'll come to see in this video is that our number system of the integers falls into this kind of Goldilocks zone where prime factorizations are in fact unique, and a subtle change to our set of numbers causes this uniqueness to break down. Furthermore, the fact that over the positive integers, prime factorizations are unique is known as the fundamental theorem of arithmetic, a rather pretentious name to carry for something which at first glance seems no more special than any other theorem. But as it turns out, this really is a special and fundamental property which underpins many of the results used by almost everyone at some point in their lives. This video is brought to you by Brilliant. More on them later in the video. To get started, the natural numbers are our counting numbers. You know, 1, 2, 3, and so on. However, I want you to imagine some alien species. Somewhat unnaturally, their number system differs from ours, in that they only count numbers whose last digit is 1, and for some arbitrary reason, they also take numbers in base 10. We will say that a number in this set of so-called unnatural numbers is irreducible if it isn't 1, and it can't be written as a product of any other two unnatural numbers. The obvious question is, are factorizations of unnatural numbers into irreducible numbers unique? Luckily, as humans, we have access to a vast variety of whole numbers, and in particular, we have access to numbers ending in 3 and 7. Why are 3 and 7 so special? Well, consider their product. This is 21, which ends in a 1, so given any two numbers ending in 3 and 7, their product will be an unnatural number. This suggests that our alien friends are missing some further ways to break down their numbers, and in fact this limitation means that we can readily construct an example of an unnatural number with two different prime factorizations. The smallest such number can be found by considering the product of 3, 7, 13, and 17, which is 4,641. By carefully pairing up these numbers, in one way this is 21 times by 221, and in another way this is 51 times by 91. All of these numbers are irreducible, and hence we have a counterexample to this factorization being unique. From the perspective of one of these aliens, this might just be a property of their numbers which is accepted as fact, and it's certainly not obvious that our natural numbers should have unique prime factorizations. We just saw that removing some of our numbers leads to unique prime factorization failing, but adding or adjoining extra numbers to our natural numbers can also cause the fundamental theorem of arithmetic to break down. Before proceeding, I need to introduce some vocabulary. Define the multiplicative identity as 1, so as you know, multiplying anything by 1 is the same as doing nothing. We say that an element of a set is a unit if it has a multiplicative inverse also in the set. That is, U is a unit if there exists some V in S such that U times by V is a multiplicative identity, 1. For example, 1 is a unit because 1 times by 1 is 1, the multiplicative identity, but 7 is not a unit because there is no such integer such that 7 times by that is 1. Then an element is irreducible if it is neither 0 nor a unit and it can't be expressed as the product of any other non-units in our set. A prime is rather awkwardly defined as an element P, where if P divides AB, then P divides A, or P divides B for all such A and B. This notion of primeness seems rather foreign, but in sets where prime factorization is unique, which are rather creatively named unique factorization domains, or UFDs, the notions of irreducibility and primeness often mean the same thing. With that out of the way, we can extend our concept of being prime or irreducible to the integers and not just the positive integers. The units of the integers are 1 and -1, which are their own multiplicative inverses. Hence, a number like -3 is irreducible, since even though it can be expressed as -1 times by 3, -1 is a unit in the integers, so really the irreducibility of 3 implies the irreducibility of -3. Now imagine extending our integers in the following way. Consider all of the numbers of the form a plus b root -5. This is denoted as z adjoin root -5, and by this point you can probably guess that this is not a UFD. Take the number 6 for example. Most people would probably say this is 2 times by 3. Maybe if you were trying to be clever, you'd say it's -2 times by -3. But to that I tell you, this is actually the same as -1 times by 2 times by -1 times by 3. And -1 is a unit in z adjoin root -5, so really this is no different to 2 times by 3. But what most certainly is different is that 6 can be written as 1 plus root -5 times by 1 minus root -5. Neither of these factors are units, and yet they are both irreducible in z adjoin root -5. This is a good example of why irreducibility doesn't imply primeness, since these factors most certainly aren't primes, and more importantly, these factorizations into irreducible numbers aren't unique. We've now seen 2 examples where prime factorizations aren't unique, but why is this property even so special and quote-unquote fundamental? I want to return to our alien friends and their unnatural numbers. They are tasked with simplifying the following fraction, 1071 over 4641. The normal way to do this in our world would be to look for common factors and cancel them off. Okay, sounds simple enough? Well, 1071 is 21 times by 51. Both of these are irreducible in the unnatural numbers, and 4641 is 21 times by 221. So, of course, the 21 cancels off, and we're left with 51 over 221. Both of these are irreducible, so yes, indeed the fraction is in its simplest form, right? You might laugh and just say, cancel off the extra factor of 17. But in the realm of the unnatural numbers, this really is a simplified fraction. But what if we instead wrote 4641 as 51 times by 91? Well, look, we can cancel off this factor of 51, leaving us with 21 over 91. These are both irreducible again, so this fraction really is simplified. Yes, in some sense, there really are 2 correct answers to the question of simplifying this fraction. Perhaps in an alien exam, a question of this sort would ask for all simplified versions of a fraction, analogous to how in our world we look for all the solutions to, say, a quadratic equation. It really is bizarre, but from the point of view of these aliens, this property of numbers would just be an accepted fact. This has been nice and all, but given that this is a video about primes, it would feel slightly wrong if the Riemann zeta function didn't even get a mention, so here it is. For those of you who don't know, the Riemann zeta function is this following infinite sum of the reciprocals of natural numbers raised to the power of s. This turns out to be equal to some infinite product involving primes, but before we even touch any of that, I want to change your mindset about expanding brackets. Suppose I ask you to expand the following infinite product, 1 plus x times by 1 plus x squared times by 1 plus x to the 4 and so on, where these exponents are powers of 2. Yes, I promise this is relevant to the main video. Imagine you're doing this by hand. The way you go from a set of brackets to a term in the expansion is you look at each bracket and you make a choice between one of the two terms. For example, I might choose x in the first bracket, then 1 in the second bracket, then x to the 4 in the third bracket, then x to the 8, then x to the 16, and then 1 for all subsequent brackets. Multiplying this out gives the term x to the power of 29. Do you notice something? That exponent of 29 comes precisely from the binary representation of 29. In other words, when expanding out this product, the way we generate each term in the expansion is by either choosing to include a power of 2 or not include a power of 2 in the exponent of x. What this means in essence is that since binary representation is unique, each power of x can be reached in precisely one way, so we end up with an expansion of 1 plus x squared plus x cubed and so on, containing every single power of x exactly once. Isn't that beautiful? Well, Euler looked at the Riemann zeta function in the exact same way. He said, well, each term 1 over n to the power of s could be thought of as writing n in its unique prime factorization. So we can say n is p1 to the power of a1 times by p2 to the a2, and so on over all primes. And since we have n to the power of s, just multiply each exponent by s. Then consider the bracket 1 plus 1 over p1 to the s, plus 1 over p1 to the 2s, plus 1 over p1 to the 3s, and so on. When we choose a term in this bracket, it's equivalent to choosing how often p1 appears in the prime factorization of n. Multiplying brackets of this form over all primes p1, p2, and so on, due to the uniqueness of prime factorization, once expanded, every natural number will appear exactly once in the expansion. We can tidy up these brackets using the sum of a geometric series. And there we have it, the miraculous formula which relates the Riemann zeta function to the most modern understanding of prime numbers. It's not so miraculous once you realize the thought process that went into finding the formula, is it? Okay, so now we know that it is not trivial that the integers are a UFD, and we also know that this property of the integers is extremely important and truly fundamental. So I think it's time to explore what's so special about the set of natural numbers which allows this prime factorization to be unique. However, given that you probably have a thirst for exploring mathematical concepts as you've made it this far into the video, today's sponsor, Brilliant, is perfect for you. Brilliant is a platform with thousands of interactive lessons in maths, data analysis, programming, and AI. They are the most effective way to learn, with their approach of teaching from the ground up and lessons filled with hands-on problem solving. There is an emphasis on doing rather than memorizing, and replacing even a few minutes of mindless scrolling a day can take your problem solving skills to the next level. One of the latest and greatest courses on Brilliant is how large language models, or LLMs, work. You will be able to learn the importance of training data, as well as how to finely tune an LLM to adjust its outputs. If all of this sounds interesting to you, then you can explore what Brilliant has to offer, free for a full 30 days, by visiting brilliant.org/PolyaMath or clicking the link in the description. You will also get 20% off an annual premium subscription. But anyways, back to the main video. The tricky thing about proving UPF is that we can't use any theorems, since most theorems rely on UPF in the first place. Everything we deduce must come from the very basics of arithmetic and numbers. It's important that the vocabulary that gets used is precise. The definition of a prime number that you've probably learnt at school is something along the lines of a number which can't be factored into anything other than 1 in itself. This exactly matches up with our definition of an irreducible element, and therefore by prime number, what we actually mean is an irreducible element in the set of integers. Now, the easy part of the proof is showing existence. That is, there is at least one prime factorization for every natural number. This can be seen by strong induction, and I'll leave this as an exercise for the viewer. The real difficulty lies in showing that these prime factorizations are unique. Let's outline how we might go about proving the uniqueness part of UPF. Suppose that there exists some n, which is the product of not necessarily different primes p1 up to pr, but is also the product of primes q1 up to qs. We can assume that these two products share no primes, since if they did, we could just cancel them off from both sides of the equation. Just pause for a moment and make sure this makes complete sense, since this will be the backbone of our proof. Now, we know that p1 divides n, since it divides our first product, so p1 must also divide our second product of q1 up to qs. But recall that strange definition of a prime element. We said that p is a prime element if when p divides ab, then p divides a or p divides b. If this is the case, then if p divides the product of a1 up to ak, then p divides at least one of a1 or a2 all the way up to ak. If you want, you can formalize this generalization with an induction argument. Now let's take a step back and see what we've actually deduced. If prime numbers are in fact prime elements of the integers, then the fact that p1 divides the product of q1 up to qs implies that p1 divides some prime qi. And the only way that two primes can divide each other is if they're equal. But this is a contradiction, since we assumed that the primes p1 up to pr and q1 up to qs were all distinct. This proof is almost perfect. We just need to fill in one gap. We must show that a prime number, or an irreducible element in the integers, is also a prime element in the integers. The proof of this dates back to the ancient Greeks, and it's so special it's known as Euclid's lemma. However, to someone who doesn't know the proof, this problem is to some degree a mathematician's worst nightmare. It's a result which most certainly is true, and yet is so frustrating to try and grasp and prove completely rigorously. Let's start by trying to find some prime number p, such that p divides ab, but p divides neither a nor b. If we look at composite numbers, you can take 6, which divides 24, but 6 divides neither 3 nor 8, which multiply to give 24. Okay, but what about primes? You'd struggle to find such a prime number, but let's suppose it exists, and in particular, let's suppose that ab is the smallest positive integer with the property that p divides ab, but p divides neither a nor b. Again, we're back to this idea of minimality. What we seek to show is that given any such ab, we can construct a smaller number than ab, say a1 b1, with the same property that p divides a1 b1, but divides neither a1 nor b1. But note there are only finitely many positive integers less than ab, but we'd have found a process which generates infinitely many smaller numbers with this property, which would contradict such an a and b existing in the first place. Firstly, observe if we replace a by a minus p, which we'll call a dash, then the number a dash times by b is ab minus pb. Since p divides both of these terms, and p doesn't divide a minus p, since p doesn't divide a, this would be precisely what we're looking for. If a was greater than p, then great, a dash is a minus p, which is positive but also less than a, and hence a dash times b would contradict the minimality of ab. Hence, we only really care about the case where a is less than p. Here a dash b is negative, since ab minus pb is negative, so let's redefine a dash. We want a dash to be less than a, but not divisible by p, So we can consider some multiple of a, say Ka, and subtract p from it. By minimality of ab, as long as k is less than b, we know that p can't divide Ka, so p can't divide Ka minus p. We also want Ka minus p to be minimal, so let k be the smallest integer such that Ka is greater than p. First, let's verify that k is in fact less than b. Since p divides ab is a multiple of p, but since p is a prime number, it can't have two non-unit factors, so ab is at least 2p. But k is the smallest integer such that k exceeds p, so Ka must be less than 2p, and hence Ka is less than ab, so k is less than b. Phew, that's a relief. Again, since k is as small as possible, k minus 1a is less than p, so Ka minus p is less than a. So indeed, if we define a dash to be Ka minus p, this is less than a. Hence, a dash b is Kab minus pb, and b divides Kab since p divides ab, and p divides pb, so p divides their difference, a dash b. And this is exactly the contradiction we were looking for. We found a number less than ab, namely a dash b, where p divides a dash b, but p divides neither a dash nor b, contradicting the minimality of ab. I realised that the last few minutes of proof have really delved into the weeds of what's going on, but care is required when setting up the foundations for close to all of the properties known in modern number theory. Just as an aside, the more common proof for Euclid's lemma is constructive, and I will quickly flash it up on the screen. Essentially, Euclid's algorithm allows us to find x and y such that px plus ay is 1, so pxb plus aby is b. So if p doesn't divide a, then it certainly divides both pxy and aby, so p divides their sum, b. Whilst this proof is shorter, the first proof is much more attainable and motivated by the basic properties of divisibility and primes. I hope now you can appreciate how fundamental the fundamental theorem of arithmetic really is.